Okay, so this is lecture, okay, let's see. This is lecture 19, and we will continue uh, Duhamel integral solution to the problem of forced vibration under general loading. Okay, so I started an example. I could not go much further. I just stated the problem we have last time, and we're going to finish it today. We have an undamped system. It is subjected to a simple triangular loading with magnitude F naught at time zero. This load is of a short duration, so TT is a small value. So we want to find the maximum displacement of this system under the action of this loading. System is undamped. Therefore, this is obviously the equation of motion. Okay. And as we said last time, for Duhamel integrals, you start by step one, writing the function in terms of a dummy variable tau. Okay. It is a discontinuous function. So there are basically three regions when um, tau is less than zero. This function f of tau is zero. When tau is greater than zero and less than td, f tau would be f naught times 1 minus tau over td. Okay. And when tau is greater than TDF tau is zero. So you have three regions, as you can see, of let's say 1, 2, and 3, and you need to evaluate the response in all of those. And the response is evaluated by using this, evaluating this Duhamel integral. Okay, f tau sine omega n t minus tau d tau for the case of an undamped system. So we start with phase one when the forcing function is zero. So this will be zero. That means the whole thing is zero. We don't have any response. Case two, f tau is f naught times 1 minus tau over td. Okay, so the function that you need to integrate, or the response that you need to evaluate, would be what? 1 m omega n integral from 0 to t of f naught times 1 minus tau over td of sine omega n t minus tau d tau. Okay, so that is the function I need to find, find, or this is the integral that I need to evaluate. Okay, if you look at this integral, you have a sign of, remember, I would emphasize again, tau is a dummy variable. Tau is a variable of the integration. T is treated basically as a constant. Okay, and of course, obviously, the eventual outcome of this would be a function of t. Okay, so the first thing to do is to break this into its trig identity. Sine of alpha minus beta is sine alpha cosine beta minus cosine beta, okay, sine alpha, okay, substitute for that. So u will become this f0 over m omega n integral from 0 to t 1 minus tau over td, okay, of sine omega n t cosine omega n tau d tau minus, okay, integral 0 to t 1 minus tau over td of cosine omega n t sine omega n tau d tau. Okay. Well, as I said, tau is the variable of integration, and t is treated as a constant. So these two come out of the integral. So this can be further simplified and be written as this f over omega n. Take this out. So I have sine omega nt integral from 0 to t of 1 minus tau over td, okay, of cosine omega n tau d tau, okay, minus this comes out. So you have cosine omega n t integral from 0 to t of 1 minus tau over td of sine omega n tau d tau. Sorry, that got a little bit messy. Okay. Now, again, I have this function of tau times this function of tau. So I should expand this in order to do the integration. So I can further simplify this, and this becomes, okay, this sine omega n t times 1 times that minus tau this times that. So you have two integrals, right? You have one integral from 0 to t of 1 times that. So that's cosine omega n tau d tau minus 1 over td, because 1 over td is a constant. So take that out of the integral 0 to t of tau cosine omega n tau d tau. Okay, so this is this first, in other words, this first integral is what I put in this bracket. For the second integral, you have minus cosine omega n t times, okay, integral 0 to t of sine omega n tau d tau minus 1 over td integral from 0 to t of tau sine omega n tau d tau. Okay? Any questions? No? So you see then the problem is reduced down basically to evaluating 4 integrals. This one, let me call that A. This one, which is similar to that in terms of ease of calculation, B. This one, I call that C, and this integral, let me call that D. So we want to evaluate A, B, C, D, substitute it in here, perform these algebraic operations, and then you have U. So let's start one by one. Okay. Any questions? No? All right. So let's go.
One question.
Yes.
In the A integral, what is that for? Um, like what's that first value? Is that C?
This is cosine of
Oh,
omega.
cosine. Okay.
Sorry.
Thank you.
Yeah, I just expanded this. So cosine. Any other question? All right. So let's move on. So I have then, let's evaluate A. A is this integral from 0 to t cosine omega n tau d tau, which is easy. Integral of cosine is of a constant times tau is 1 over that constant, right, times sine of omega n tau, evaluated from 0 to t. Substitute for t, this would be 1 over omega n sine omega n t. 0 sine of 0 is 0. So that's it. So that's A. B is this integral from 0 to t of sine omega n tau d tau. Okay. Integral of sine is -1 over omega n cosine omega n tau, evaluated from 0 to t. So substitute that. You have -1 over omega n cosine of omega n t minus minus, of course, would be plus 1 over omega n cosine of 0, which is 1. So this would be 1 over omega n. I rewrite it this way, minus 1 over omega n cosine of omega n t. Okay. So that's the first two integrals. Let's now go to the third one, C. That is an integral of this form, tau cosine omega n tau d tau. How do you evaluate that integral? Remember from calculus, this is a product of two functions, so we need to use the integration by part. What was integration by part? Okay, integral of u dv is, if you consider one of those two functions that are multiplied as u, the other one as dv, integral of u dv is always u v evaluated for those bonds minus the integral of v du. The trick is which one to choose as u, which one to choose as dv. We consider this as u, this as dv. Okay, so u is tau, so du would be d tau. dv is this cosine omega n d tau. So v would be the integral of that, which would be 1 over omega n sine omega n tau. Okay, substitute this in that. So you have the integral of a to b of u dv, okay, u dv would be uv. So we have tau over omega n sine omega n tau from a to b, 0 to t, minus the integral of a to b of what? V du. This is v, this is du. So it would be 1 over omega n of sine omega n tau d tau. Okay, so this is easy now to evaluate. That's tau. I mean, substitute for tau t, so it would be omega n sine omega n t minus t, t over omega n sine of 0, which is 0, right? This one, you have what? Negative 1 over omega n cosine omega n tau evaluated from 0 to t. So substitute for that, you get t over omega n sine omega n t minus plus 1 over omega n, which is 1 over omega n squared, times cosine omega n t minus 1. That's the outcome. So this is integral C. So let me label these. This was A, this is B, and this is C. One more integral to evaluate, that is D. D is an integral from 0 to t, tau sine omega n tau d tau. Okay, again, consider this as u, okay, and this as dv. So u is tau, du is d tau, dv is sine omega n tau d tau, and v would be negative 1 over omega n cosine omega n tau. Okay, so substitute again. Integral of u dv, okay, is u times v, okay, which is negative tau over omega n cosine omega n tau from 0 to t, plus the integral from 0 to t of v du. So you have negative coming out of that. So you have, okay, so you have, because this is negative, right? So negative would be positive. That will be 1 over omega n cosine omega n tau d tau. Okay, so this would be, substitute for t would be negative t over omega n cosine of omega n t minus cosine 0, and this would be 0, so it would be 0 for that value, plus, okay, if you evaluate this, would be 1 over omega n times 1 over omega n sine omega n tau from 0 to t, and simplifying all of that would give you negative over t over omega n cosine omega n t plus 1 over omega n squared sine omega n t. Okay, so this is integral d. So remember, we need to substitute all of those into this equation. So I will just simply do that. Okay, and that is, okay, going to give me, okay, so let's do that. Okay, so I'm going to do the substitution in here. So let's do that. I will have, okay, u is f over m omega n times sine omega n t times a plus c. This is a and this is c. So that would be 1 over omega n sine omega n t. This is a, okay, and c is, okay, negative t over omega n, okay, t d, because you have this, remember, 1 over td, so 1 over td multiplied by c, and that will give you this sine omega n t minus 1 over omega n squared t d times cosine of omega n t plus 1 over omega n t squared t d. So that's sine times a plus c minus cosine omega n t times integral b and d's, sum of b and d, which is 1 over omega n minus 1 over omega n cosine omega n t plus t over omega n td cosine omega n t minus 1 over omega n squared td sine omega n t. So all I did, let me repeat, I just substituted A, B, and C in here. So that's going to be the response. You can see that you can take 1 over omega n, factor that out, comes out of this bracket. So you'll have 1 over m omega n squared. Omega n squared is k over m. So substitute for that, you will see that un would be, okay, reduced to this form. And after all the simplifications, you can see that you can simplify all of these. And there are a lot of common terms that, you can factor things out. Omega n and sine of omega n t. And after all that simplification done, you get this function, 1 minus t over t d plus 1 over omega n t d sine omega n t minus cosine omega n t. So response of the system when you have the forcing function still acting on the system. In other words, anywhere from here to here, anywhere from here to here, t is greater than 0, less than td, is given by this function. Now, how do you find the response after this point? You have two options. One, in other words, this is, if I want to make sure that we are following, this is for the case of, I broke this down to 1, 2, 3, right? So this was for the case 2. Now, for case 3, how do I find the response? Well, you do perform, I mean, the obvious, approach would be, do you apply Duhamel integral to all these regions? So if you do that, in other words, you have u is going to be 1 over m omega n, Duhamel integral from here to here, 0 to td, where obviously this is a forcing function, okay, sine omega n t minus tau t tau, plus that integral evaluated from td to anywhere, okay, for that region, sine omega n t minus tau d tau. Obviously, in this region, this is 0. So you only need to evaluate this integral. But if you look at that integral, okay, you've already done that for the general case was this where you had 0 to t. So you don't have to redo the whole integration. Just look at the results for A, B, C, and D and substitute for t, td, replace t with td, and you see that you end up with this function if you do that, f0 over k times, in other words, in here, I just substitute for t to be td, okay, not here, a step before that. So this is what you get, sine of omega n t times 1 over omega n td, okay, cosine omega n t d plus 1 over omega n t d, okay, minus cosine omega n t times 1 minus 1 over omega n td sine omega n t d, okay? So that's the response for part 3 when the forcing function has been terminated or the system is experiencing a free vibration, okay? You didn't have to go through this process, of course, of re-evaluating this integral. You can do it an easier way. How? You know that this function describes the response anywhere from here to here, including at that point. So what happens in this region? You have a free vibration starting at this point due to the initial conditions at this point. What are the initial conditions here? That is, what is the displacement and velocity here? If you can evaluate those, then since you have a free vibration, you remember free vibration is what? in terms of initial conditions. U initial condition cosine omega nt plus u dot naught, which is initial velocity, times sine omega n t. How do you find u and u naught? By doing what? Substitute here for t is equal to td. Okay, so this and that cancels out, and this would be cosine omega td minus cosine omega td. That'll be u at t equal to td. Then you need to take the derivative of this and equate t is equal to td, and that'll give you u dot naught. If you do that, you can easily see that basically what happens is this is going to be this is going to be your u dot naught over omega n, and this is that u naught, the initial conditions. So that's another way of doing that. So in other words, you could have reached the same result by using this relationship, finding u at this point and u dot at this point, and then substitute them into this equation, and you get the same results. But anyhow, you have these two functions now, representing the response of the system, okay, while the force is acting on the system and after the force has a stop. Now, how do you find where the function is maximum? Because that's what the problem is asking. Find u max. Okay, it's very easy to find where the maximum value occurs here during the free vibration time. Why? Let me show you. You remember, if this is alpha, this is beta. Okay, so for this case, you have what? You have u is equal to f naught over k times sine omega nt alpha plus cosine omega nt beta, right? So how do I find the maximum value of this function? Anybody, can you remember how we do it?
Take the derivative and say
You don't have to take derivative and equate that to zero to find the time corresponding to that and put it into this equation to find the maximum u. You can see that very easily what the maximum value of this function would be, right? Remember, you can always write this as if this is a cosine of something, and this is a sine of something. So this whole thing comes down to what? Writing it as a squared plus b squared times 1 over this sine plus 1 over this cosine. In other words, this is alpha, this is beta, right? Since, square root of alpha squared plus beta squared is always, this over this is always 1. This is a sine, that's a cosine of function. So this would be the sine of something. So the amplitude of this function can be easily found, and that is the maximum value of the response. Okay? We've done that many times. So for this function, okay, you can always find the maximum value very quickly. But how about for this form? For this one, you need to take the derivative, equate that to zero. You find the time at which this function is maximum. Substitute that time into this equation and you find the maximum value, and then you compare the two. If you do that, and I want you to do that, go through that practice and show me whether the maximum occurs after the force has been terminated or before that, if you have a small time. Okay. So also, let's make another observation here. You remember we were talking about dynamic load factor? Look here. If you have a constant load of magnitude F naught instead of this triangular load applied to the system, which has a short duration, what is this? This is the corresponding static displacement. So this is your magnification factor or dynamic load factor. Okay. Especially if you can find that for maximum value times this, that would be dynamic load factor. So for Duhamel integral, we can also, or not Duhamel integral, for any general function, we did that for impact load last time, right? Which we found dynamic load factor was 2. If you take the derivative of this, okay, equate that to 0, find the U max, okay, you have something times this, and that something term is your dynamic load factor that compares the displacement under a constant load F naught to a, in this case, triangular load. Okay. So with that said, you can see that finding the response of a system under a general loading function, even if you have a simple loading like this, involves many steps of long integrations. Okay, I wanted to do another problem, um, but you have doesn't mean that you have no other choice. We will see that there are easier ways to evaluate this Duhamel integral, or even find the maximum response of a system, of course, without going through all these difficulties. But I want to also present another problem, which we won't be able to solve that um, today, but at least I will set it up. It's a good practical problem. And I want you to start working on that if as a sort of a good practice. And we will do that next time. Next time will be next Wednesday. Remember, no class on Monday. You're going to work on your exams. So let's say we have a problem. This is a water tower, okay, with a water weighing, let's say, 100,000 pound force. The stiffness of the column is given at, let's say, 3 times 10 to the 5 pound per inch. Okay. So this water tower is subjected to a blast loading with a very short duration. Let's call that T naught is only 0.03 second. So the half is a symmetric load. So half of that would be this duration is 0.015. Okay. Um, so we want to find again the maximum displacement of this system. We are concerned when that maximum displacement would occur while the force is acting or after the force has been terminated, or whether it's going to happen here, here, or here. 3 possibilities: 1, 2, and 3. Okay, so we want to find that out. Um, I know we don't have time to do this, but let's at least set up some of the basics. Um, the mass is given is 100,000 pound force. So let's convert that to, I'm sorry, this is the weight that is given. So divided by 380.6, that'll give you the mass, okay, which comes out to be 258.8 inch, pound mass, okay. K is given as 3 times 10 to the 5 pound per inch. So we can find omega n, which we will need, K over M, that will be 34.1 radius per second. And so um, uh, the integral, the response that we need to evaluate would be 1 over m omega n integral from 0 to t of f of tau, okay, sine omega n t minus tau d tau, okay? So the step one is setting up the forcing function for all regions. And in this case, we have three regions here, here, and here. So I will set those up. For the first region, okay, the equation would be like this. If you do that, evaluate that, would be 2f tau over t naught when tau is greater than 0 and less than t0 over 2. For this region would be 2f naught times 1 minus tau over T naught, okay, when tau is greater than T naught over 2 and is less than T naught. And after that, obviously, when tau is greater than T naught would be 0. So compare that with the previous case we did. Now we need to evaluate uh, this integral for all these three cases. And let me call them 1, 2, and 3. I don't think we will have time to finish that, but at least let's set up just for case 1. So for case 1, when tau is greater than 0, less than t0 over 2, you have u is 1 over m omega n integral from 0 to t of 2f naught tau over t naught sine omega n t minus tau d tau. Okay. Okay. I'm going to stop here. I know that there's enough time, but the good news is this. You may think that I'm going to perform now again this integration and the other integrations. The answer is no. There is a table where you can find this integral, convolution integral, for some common functions, such as, for instance, this, or this, or this, or this, or there are like 20 cases that have been tabulated, and I will, in fact, provide you that table.
Can you
So,
shift your paper up a little bit?
oh, sorry about that. So when you are given a Duhamel integral, you don't have to do all that integration unless I'm asking you to do it, or at least you can use that table to verify your answer. So with that said, I'm going to stop here. I will finish this problem, which is a very good problem, next time, and then we'll continue. But have a great weekend. For those of you who want to see me during my office hours, please do so. I will be there. Uh, Otherwise, I will just see you on Wednesday. Have a great weekend.
Thank you.
Thank you.
Thank you.
Professor, quick question.
You know what? I just realized something terrible happened. No, I
Hmm?
don't know if I had done the recording.
It says it's recording.
It
I
is
think you still
recording.
have it.
Good. So let me. Oh, I'm glad.